Hello everyone and welcome to video number 3. Today we'll be speaking about the fundamentals of econometrics for our purposes. In particular, this means looking at how we can derive the line of best fits given some data between, well, at least two variables. And the idea of correlation not being causation. Under what premises can we know that one variable causes the other and not merely be just correlated with another variable. This is important for our purposes simply because we are going to be dealing a lot with data in this course, or at least we're going to see a lot of data. We're going to be doing nothing fancy with data. Our use of econometrics is not going to be very rigorous or mathematical, but we still need to understand exactly what pitfalls to look out for in interpreting data, especially because good econometrics informs good policy, and likewise bad econometrics informs bad policy. So at least let's cover the basics, the very basics. So if you are familiar with econometrics, you may wish to skim through this video. If you're not, please do stick around if you feel at all shaky about this kind of material. As I mentioned, we'll be looking at deriving the line of best fits. We'll also speak about how we can measure the goodness of the line of best fits. We'll then also look at some cases where, well, essentially you can see biases introduced into the analysis, which makes for bad econometrics. And we'll be speaking about this in greater detail on Thursday after our readings, one of Cassidy and the other of Lavoir's inputs. So let's see. I'm going to minimize my video here and let's take it away. So here we'll simply take the simplest example I could think of in motivating this topic. And it comes from Stock and Watson's textbook, Introduction to Econometrics. Maybe you are already familiar with this. I find it a neat example because it's a well-specified question. And the question is as follows. You've got the governor of a district in California, and he or she wants to know if he or she reduces the class size, which we see here on the x-axis, what will happen to the test score? The governor wants to increase the test score, wants to have better grades on average, but he's unsure, she's unsure, the effect, the size of the effect. Okay, I'm just checking, yeah. So we have our scatter plots, and we see that there's no obvious immediate relation between the two. Perhaps you can notice a bit of a downward trend looking at these points, but overall it's not immediately obvious what the trend is. So what we would like to do is fit a line that in some sense represents that relation between those two variables. And here we're getting at the concept of a line of best fits. But let's speak a little bit more about how we can derive this line. So we know that a line has a simple structure or simple form. It is usually of the form, well, y is equal to the intercept with the y-axis plus the slope times, well, the independent variable, right? And this is what we have up here. Our independent variable is the class size, the students per teacher. Here we have the output variable, the test score. This is what we would like to increase as much as possible. And here the slope, beta 1, well, this is the effect of, let's say, decreasing the class size by 1 student per teacher. So reducing the class size, the effect on the test score should be given by beta 1 here. That's just some number which we would like to know. Beta 0, on the other hand, is the intercept with the y-axis. It's, well, the value of the test score when the class size is 0. So when this cancels out. We also know that class size is not the only thing that affects the test score. So all the other variables that may affect the test score, we've just aggregated them, we put them together over here, and we've called them other factors. Yeah? And we just represented then these variables by letters, as we usually do in math. So test score is now y, class size is X, and all those other factors we've just called U. And we see we have I here as the subscript, as it tells us that we have different districts in California. Looking at our graph again, well, there's dozens, maybe hundreds of districts that we have data for. So this is districts, I don't know, 20, and it has a students per teacher ratio of what looks like 25, and an average test score on that district of 622 or whatever it may be. And each of the dots represents one district. Okay, so given this equation, well, what does it really represent? Well, here we've written our equation again, except now we have a different scatter plot, a general one. I'm not saying necessarily what it is, we just have y and x. We know that beta 1 is the slope, given by our blue line here. And for the time being, I've just drawn in any blue line, any line at all. This is not necessarily the line of best fits, it's just any line. And what we'd like to do is change the slope and shift it around such that it becomes the best fitting line. Well, let's first interpret what U means, because perhaps that is the one that makes you might be least familiar with. Well, here we can kind of understand what U is. U is the difference between the fitted line, so here, and the actual value, which is here. So for U1, for this district here, you will have this size of the error. So U is the error. It's by how much the fitted value up here is off from the actual value. And then for U2, you see this is the error term. And for U3, this is the error term. It's simply the distance between that dot or those dots and the line that we fit. Beta 0 is the intercept. We can't quite see it on this graph because we don't have the y-axis fitted here, but it would be around here if we were to draw the y-axis at 0, right? Okay, so we know some values of x and y. We just need to find those values beta 0 and beta 1. And when we do so, then we'll have some idea of the effect of the class size on the test score. We'll have some idea of what beta 1 is, what the slope is. And that will better inform the governor's policy. But we can draw many lines, right? Here I've drawn a second line, this one in orange. And well, just by looking at it, I have no idea of which one fits better. And we haven't even defined the criteria under which, by which we mean fits better. Well, we can begin to do so by recognizing that the line that fits best is the one that minimizes those errors. So if we just zoom in, or at least focus on this part over here, we've got our two randomly drawn lines essentially, and we see that given the first actual value, our first blue line is closer to that actual value than this orange line. So the error term for the blue line is actually smaller, looking at the first observation alone, than this second orange line. And if we were to do that for compare the errors for each and every data points, then we could say, well, the line that has minimized the errors, or the sum of the errors, is the line that fits best. Therefore, we have defined the criteria by which we mean the line of best fit. The line of best fit is the one that minimizes the errors. So if this is smaller than that, then that's great. And then we do it for each and every dot. Let's look at, say, this dot down here. Well, the orange line is much closer than the blue line here. So now the orange line is, well, gives a smaller error term than when we look at this observation alone. So we need to somehow add up all these errors. But immediately, you may spot a problem. Some errors will be positive, and others may be negative. We can't just sum them up, not in a straightforward fashion. Well, to give an example, have a look at that blue line again, and we see that the error term here, well, this is negative, right? The error term is actually, the fitted value is above what the actual value is. But then we have the opposite case here. So if we had these errors will begin to cancel each other out, and they could perfectly cancel each other out, even though there is not a perfectly fitting line. So we can't just sum up the errors as they stand, because we're summing up positives and negatives. So what we'd like to do ideally is sum up their absolute value. We're just interested in the size of those error terms. But rather than doing absolute value, we could equally do just adding up the squares of these error terms. Because if we add up, well, a square is always a positive value. So the square of this error term plus the square of this error term plus the square of this error term and so on will always give us a positive value that reflects, to some extent, the goodness of the fits. It reflects how well the line fits. So that's why we have this expression down here. If we sum up the squares of the errors, they won't simply cancel out. So what we're essentially trying to do when finding the line of best fits is minimizing the sum of squared errors. This is all this expression is saying down here. If we minimize the sum of squared errors, we will find the line of best fits. Okay, now we can skip through this part. It's really not so necessary for our purposes. It's a bit more mathematical. I'll leave it in the slides in case you are interested. But essentially all I would like to show is that what we are doing when finding beta 0 and beta 1 is really just using the data that we have. So we have data on y and x, and we can use that with this logic to find beta 0, beta 1. Excel does it for you, of course, when you put in the line of best fits. But I would like to just simply demystify this. Essentially all you're doing is taking this objective of minimizing u squared, and then we're using the data that we have on y and x, and we're trying to find b0 and b1, where these b0 and b1 are any estimates of the true coefficients. And the values of b0 and b1 that minimize this expression will be our best estimates of beta 0 and beta 1. If you know a bit of calculus, you know that you can do this task of minimization through just taking the derivative of the expression. Remember, this is just the error term expressed in terms of y and x, and setting them equal to 0. After you do so, you'll be able to rearrange for the variables that you are unfamiliar with, beta 0 and beta 1. Now, these just have a hat on them at the moment, because the hat just signifies that these are estimators of the true coefficients. It's the best estimation we can get under the current method of trying to find the line of best fit. Okay, so we can kind of skip through the maths, but essentially you're just using a bit of calculus and you find that you can solve for these estimators. And they're purely in terms of the data that we have. X, remember, in our example, was the class size and y was the test score. And here with the bar is just the average. So here you have some notion of the variance and the covariance, and here you just have the averages that give you beta 0. So these beta 1 and beta 0 numbers that give you the line of best fits follow from this process of minimizing those sum of squared errors. And that's what your Excel program or whatever software you may be using is doing when you are trying to find that line of best fits. Okay, so that's, like I said, that's what Excel is doing behind the scenes. And here we have simply what Excel has given me when I try to find the line of best fits. Remember, this, albeit a neat expression for what you need to do in order to find these coefficients, would be extremely arduous to work out by hand, right? So it's nice to have a program like Excel or Stata or R to find that to basically do these computations and straight away just show you that line. So here we have the line given in red, and we see indeed it is negatively inclined as we might have expected, or as we hypothesized, if you like. So this shows that yes, as you have fewer students per teacher, as the class size decreases, our test score seems to rise. There is a negative correlation between these two variables. The negative correlation is found here, or we can see it here. where the beta 1 value that we found, this guy, or estimator of beta 1, is a negative number. Here we have a beta 0 value, which is 698. Perhaps this doesn't have so much meaning, right? Because this is the value we'd expect the test score to be if there were 0 students per teacher. So don't think too deeply about what beta 0 is telling you, or at least don't expect a test score of near 700 if you have 0 students per teacher, because there are no teachers, there are no students to take a test, right? But it just simply helps us define this line. For our purposes, we're much more interested in this beta 1 estimate, the minus 2.2, right? The slope of this red line that we derive from finding the minimized sum of squared errors. Okay, so in answer to our governor's question, at first glance, it seems that if we reduce the number of students per teacher by 1, the average test score will go up by 2.28. So if we go from 20 to 19, the test score should go from, let's say, 633 or something like that to 636, or 635.28, right? Okay, so are we done? Can we go back to our governor and say, yes, we found a negative correlation, reduce that class size, and you will certainly 100% increase the test score. The data says so. Well, no, we're not quite done, right? This is just the first step. We have many ways in which our sort of reasoning could be a bit faulty. So we're just going to investigate those reasons. Well, firstly, we have a line, and it is negatively sloped. But firstly, we'd like to know, well, how well does it fit? Is this line negatively sloped but doesn't describe the data so well? Or does it describe the data very well? You can see that with our negative slope, we still have dots all around this line. So does this line describe this dot? Yeah, it describes it quite well. Does it describe this dot? Well, no, it's really quite off. The error term is still quite massive here, even though we've minimized the distance as a whole. So what we'd like to do is somehow give an expression for how strong this relation is. And this is what we call the R squared does. Whenever you see an R squared, at least know at the basics that if you have an R squared of 0, you've got the worst fit possible. Yeah, you've got a line which doesn't really that shows no real relation between the x and y variables. And if you've got an R squared of 1, then essentially all the dots happen to line up perfectly with your line of best fits. They are essentially on the line of best fit at all points. Here's the maths behind this variable that we are now defining. And it is simply the ratio of what is called the explained sum of squares to the total sum of squares. The explained sum of squares is the distance between our fitted variable, so let's say here, and the average, which we have here on the orange line. And we do this for every fitted variable. So for this, so here we've got the fitted value for this one, which is clearly off by quite a bit. And we subtract the average, and we see, well, here's the gap, and we do that for every dot along the way. And we compare it to the actual gap between the actual value and the mean. And what essentially the R squared is telling us is, has our line of best fits given us more information between these two variables than simply taking the average? So if there was no relationship between these two variables, then to understand the test score, the sort of distribution of test scores, if there was no relation, then we would expect there to be not much of a trend to discern, and we may as well just know the average value of the test score. That's going to give us as much information as we could possibly have. Knowing anything about the x values tells us nothing more than simply the average outputs. So That's why we're comparing it to the average at all times. If X tells us much more information about the test score, and there's more of a strict trend, then we would expect the R-squared to go up, and we have an improvement upon the simple average. And we see, well, in our case, there is an improvement, and in fact, we find an R-squared of 0.05. Essentially, what this is saying is that 5% of the variation in Y, in this output, is explained by this input, by having knowledge about or having data on the students per teacher. So having knowledge, having some information on the students per teacher actually gives us a better idea of what the test score will be. So if I know, let's say that the students per teacher is 25, then I expect the test score to be lower than average. And sure enough, it is. So in that sense, a line of best fit is giving us more information. So that's essentially what the line of best fit, the R-squared is telling us. It's a sort of quantification of the goodness of fits. Okay, so we return to our question that, well, we see this correlation between those two variables. When our students per teacher ratio goes down by 1, then our test score seems to go up by 2.28. But can we therefore conclude that this is what will happen if the governor puts in policies that reduce the class size, that will certainly get an increase in the test score? Well, there's a lot of extra analysis that we need to do in order to ensure that this line of causation that we expect to be happening actually is happening. In particular, we need to focus on this number here, our value of beta 1, our estimate of beta 1, the effect of X on Y, and ask ourselves, well, is it just merely by chance that we are finding such an estimate? If we were to use data from different years of the same districts under the same conditions and so on, would we find actually, no, if you run the analysis again with this different set of data, no, it's actually closer to 0 or is 0 or is positive. If we had multiple estimates using the same analysis, perhaps we could find that we get different values. So we need a way of kind of comparing the value that we found to 0, to no effect, and seeing how likely it is that we find an effect and find an effect of this size before we can conclude on whether or not we can expect this variable to cause that variable. So we need to set up an hypothesis. Like I said, perhaps it's merely by chance, given the data that we have that we find as beta 1. Perhaps if we had different data, we'd get 0 20 times, and we only get minus 2.27 this one time. So perhaps it's just unlikely that we got this. So what we do to check this is say, well, let's make the hypothesis that the true effect of X on Y is 0. And the alternative hypothesis is, well, it's not 0. There is some effect. The truth is that the X variable student-teacher ratio does affect the test score. Then we can say, well, if we assume that the values, the estimates of beta 1 are normally distributed, we can actually then calculate the probability that our estimate that we found is so far away from 0. So let's look at what I mean by that. Here we have a normal distribution. It's one of these bell curves. And here we have the null hypothesis that the true value is 0. And because it's the true value, this is what we expect to get most of the time. And if we had the best data available for the biggest sample size, then we are really extremely likely to get around here. But we have found a value which is down out here, right? Which, given our distribution, because we know how these values, these estimates of the true value of beta 1 are distributed, we know the probability that we find the value that we found. And the value is given on this y-axis. Okay, So this is the idea of statistical significance. It's the probability that you find a value which is so far away from zero. And if it's so far away from zero, if the probability of finding this value is so low, let's say it's 0.001, so there's like a tenth of a percent that you will find such a value, then perhaps our null hypothesis that the true effect is zero is simply wrong. In fact, we have, if this is a 1% chance of finding such a value, then with 99% likelihood, the null hypothesis is, we can reject it. We can say, no, it's not correct. There is a non-zero effect of class size on the test score. In order to actually calculate this probability, we need to know a little bit more about the distribution. And this is where the standard error comes in. The standard error tells us about the shape of the normal distribution, or about the spread of the set of possible results. If the standard error is really big, a really big number, then we expect the bell curve to be kind of flattened and and kind of fattened. Yeah, so it will be kind of shifted out, and it will look more like this. Now, the standard error is simply a way of comparing between different distributions how far away these extreme values are. So between one standard error, we have around 68.2% of all observations, all estimates that we find fall within between these values. But if we have, say, 2 standard errors, then we have a value out here, then we know that, well, there's only a 95.4% chance that we'll find an observation. Well, there's a 95.4% chance we'll find an observation that falls between 0 and 2 standard errors on either side. If our value is down out here, then there's less than 4.6% chance we'll find it if the null hypothesis is true. So given that setup, if we find an estimate down here, then it's likely that the null hypothesis is false and we can reject it. We can never know for sure, but it just becomes more and more likely the further we get away, the greater the number of standard errors we are away from the mean of the distribution, which in our case here is 0. So coming back to our example, let's suppose that we know somehow that the distribution has a standard error of 1. That makes the maths easy. We know that, well, between 2 standard errors, more than 95% of observations are found. Well, now we're outside of 2 standard errors, so we know that the chance of finding this the probability of getting such a value by chance alone is less than 5%. So we say we can reject the hypothesis that there's a 0 effect with a 5% at the 5% level. So it's statistically and significantly different from 0 at the 5% level. We have a way of quantifying how sure we are that our results are not being driven by chance and chance alone. Now, in reality, getting the distribution right, knowing that it's normally distributed and finding the standard error can be quite difficult, but at least understand that the statistical significance is a really important concept here. Okay. So now we're assuming that we have statistical significance, and we can reject the null hypothesis that there is a 0 effect of class size on the test score. A more, a bigger concern for our analysis is perhaps there may be other variables that determine both class size and the test score. So, for example, what if districts with higher income have smaller class sizes because, let's say, parents are very happy to pay for private schools with smaller class sizes, and also those same districts with higher income levels have better test scores because parents take their kids and put them in after school classes and ensure they have best access to resources and materials and so on. So it could be under this premise that higher income drives smaller class sizes and better test scores. So this presents a problem for our analysis, because then the effect that we find here in beta 1 is merely a misinterpretation of what's really going on. Because really what's going on is there's something here in U which is driving this and is correlated with this. In fact, it's driving this too. And that therefore, if we expect change in class size will change test score, we're actually mistaken. So what I've done here is actually, well, just graph that data. Here's the average income in the district. It's using the data from Stock and Watson. And again, we have the test score on the y-axis. And sure enough, we find that there is a positive relationship between the average income and the test score in any district, as we might expect. Those districts that are richer have better test scores. In fact, this relationship is non-linear. It seems to be best described by some logarithmic function. You have a fairly high R squared. It's explaining a lot of the variation. But nonetheless, for our purposes, we can just see that it's positive. Okay, so income, at least at first glance, seems to be driving test scores, determining the test scores. Do richer districts also have smaller class sizes? Well, it seems that the class size does go down as incomes increase. So this is again just sort of eyeballing the data, but it seems that there is that relation that we expect. So here we have a problem. There's an omitted variable, namely income, which could be determining test scores and correlated with class sizes. So that might mess up our analysis. You have to be careful of that. We could also look at, say, educational background instead of income. And we see that, yes, educational background, say, captured in the percentage of students learning English as a second language. Well, the districts that have the greatest number of students with English as a second language also have lowest test scores. So, again, it's a case where an omitted variable could be driving the test scores, and it appears to be correlated with the class size as well, and that could mess up our analysis, or at least mess up our interpretation that there's a causal relation, as we at first thought. So that's all summarized here. If we don't take these things into account, lowering the student-teacher ratio will not necessarily cause a higher test score, and we will be misinforming and misguiding our governor. Okay, we won't go into doing all the econometric techniques necessary in order to capture and control for those extra variables which absolutely should be done. We will just simply look at the table found in Stock and Watson, where they simply do this, and we'll just interpret what their table says. Because you may be reading a few papers in this course, you may come across some papers where you see some econometric analysis, and I would at least at the very basic, at the very least, I would like you to understand what these tables are saying. So here we have got the dependent variable, right? This is the average test score in district. This was on our y-axis. And here we have the variable of interest. This is the student-teacher ratio, and we would like to see the effect, the coefficient on this variable. So in our analysis, where we have no other control variables, we find that the beta 1 coefficient is minus 2.28. This is what we found when I just ran the line of best fits in Excel, minus 2.28. So we're in agreement, well, you can see where that comes from. But of course, we need to control for these other variables. And when we control for the percentage of English learners, for example, so the educational background in some sense, we find that our estimates of the student-teacher ratio, the effect of the student-teacher ratio on the average test score goes down substantially. Yeah, it goes down from minus 2.28 to minus 1.1 in this specification, in this regression. And indeed, the R squared, the goodness of fits, improves quite a lot. So now we're explaining more of the variation in the output variable, in more of the variation in the average test score between districts. much more, 42% as opposed to around 5%. Notice that in the brackets here, we have a number, 0.52 here. This is, as you see here, this is the standard error. And as we saw earlier, if our estimate is above 2 standard errors, so 2 standard errors here would be around 1, right? Or minus 1. If our estimate is greater than that in absolute value, then we know that our estimate is statistically significant. And that's what these little stars mean here. You see in the footnote here, if it's got 1 star, then it's significant at the 5% level. And if it's got 2 stars, it's statistically significant at the 1% level. So the more stars, the more likely we can kind of believe in this, or at least the more reason we have to see this as a reasonable estimate. The more, the fuller the specification, like in columns 3, 4, and 5, perhaps the more likely we can rely on our analysis because we're controlling for more and more effects. Although it's not quite as simple as that, usually we would like to control for as many variables as possible. And we see indeed that the R squared goes up, showing that our specification is increasing the amount of the variation in the output variable that we can explain. So you see that our original estimate of minus 2.28, when controlling for other variables, like the income variables here, goes down substantially to only minus 1. So perhaps, given this information, the governor would not like to try to reduce the class size. But with this information, maybe the governor would. So we can already see that the quality of the econometrics really can affect the policy. Right? Okay, so to sum up, we have some sources of bias that we have implicitly come across that we really need to control for or be aware of in order to make sure our empirical analysis is correct. So we have what's called omitted variable bias. This is the examples where you don't control for these sorts of variables and you just take this as the right estimates. Well, here we have in specification 1, omitted variable bias. And the size of that bias is related to the differences in these estimates. So we don't want to leave out variables that determine our output variable and are correlated with our independent variable. We also have a source of bias which is functional form misspecification. This is where you just assume that the relationship between one variable and another is, say, linear, when in reality maybe it's non-linear. Like the effect of income on test scores. Here we see that the higher income districts do have higher test scores, but it seems at a level to kind of plateau. So that after maybe $30,000 or $40,000 per household in a certain district, there are basically no more increases in the test score. You're kind of maxed out already. Whereas at the beginning, yeah, differences actually matter quite a bit. So here this linear form is not the best function to fit between these data. Rather, perhaps a log form. But this is, again, something where you can only have a look at the data and kind of guess or have a educated guess as to what the linear or what the best functional form is. Here we have with a log form, and we see that in fact the R squared goes up. So the R squared can kind of give us some information about what the functional form might actually be for the true parameter value. We have other sources of bias which arise when you mismeasure the independent variable in particular. And we won't go into this in too much detail. You can have sample selection bias. So that's when the way you collect your data systemically excludes some of the necessary data. For example, if a pollster is trying to predict the American 2020 presidential results by surveying the US population through calling landline phones, there will be a problem. Unfortunately, this is not interactive class where I can talk to you about what that problem may be. But okay, the problem is, well, there aren't many young people these days who bother to install a landline phone anymore. We're all using mobile phones. So if you're only calling through landline phones, you're probably going to only speak to old people in the US, and therefore, if there's a correlation whereby older people are more likely to vote for Republican, maybe, then you're going to get a biased sample, and that will bias your estimates. So sample selection bias is a problem there. Lastly, we have simultaneous causality bias. So it's not only the case where X causes Y, but also Y causes X. If you have one of these issues of simultaneity, then you've got another source of bias. Here we've got an example where, suppose the government introduced a program where districts with low test scores automatically receive more funding for teachers. So now we have the case that test scores actually cause class size. It goes the other way. And if we're not aware of this, we're not trying to adjust for this, then we will bias our estimates. In summary, internal validity, just to define some of these terms that are important. Internal validity means there are no sources of bias in our regression analysis. We've dealt with all these biases here, and it's as sort of legitimate as can be. External validity, on the other hand, refers to the situation where the results of the regression analysis can be used to inform us of a setting or a different population than the one we have analyzed. So for example, if analysis of the student-teacher ratio in California give us some information about test scores there, then that's great, but I'm interested in New York, then we could say that the external validity may not hold. If it's New York and it's 30 years later and there's institutional differences between these settings, then maybe there is no external validity that we can apply there. Otherwise, on the other hand, if these are similar, then perhaps we could say there is external validity. Many other econometric problems exist. This is really just a taste of econometrics in some sense, and at least kind of outlining the main problems, if you like. For example, an estimator may be unbiased, but it's still inconsistent if we have the wrong standard errors. So we could therefore have an incorrect picture of what is statistically significant. So there are obviously much more concepts to go into if you would really like to understand econometrics. This is just a first taste, but hopefully you can see what we're doing when we are in looking into these correlations and seeing that correlation isn't always causation. Okay, for policy implications, as I said, good policy is heavily dependent upon sound econometrics. Yet, the more complex the system, the harder it is to truly know if we have accounted for all sources of bias. So, in some sense, that's why I've started with this instance or this example where you have student-teacher ratio and the test score, because it's small, it's well-defined, perhaps there isn't so much simultaneity, it's not super complex, relatively speaking. If you start thinking about macroeconomies, international economics, perhaps more complex systems, then it's harder to know if you've accounted for everything. For example, here we have the Phillips curve, the relationship between inflation on the y-axis and unemployment. So if we're looking at this relationship, which is definitely very important from a policy-making perspective, then and you want to know the relationship between the two, and the government looks to change unemployment by spending in order to change inflation, then we'd want to make sure we have this correctly specified and have done the regression as well as possible, so that we get the best estimate of beta 1. So in this example, omitted variable bias concerns might be, well, is there something that drives inflation that is correlated with unemployment? You could think about the interest rates, you could think about union density, other institutional factors. There are various things which, if not controlled for, would give us a bad estimate of beta 1. Similarly, maybe unemployment isn't well defined or isn't measured so well. That's perhaps less of an issue. Simultaneity bias, well, it could be that inflation is causing unemployment through some channel that we haven't thought of. Another important one is the functional form. is the relationship linear, or is it like this, in this sort of non-linear form? I'm not so sure. Okay. In some econometrics and macroeconomics is messy. That's, I guess, one of the big takeaways here. It always demands a critical assessment of data, and due to its nature, it leaves room for biases, as we have seen. Also of other kinds of biases, which we will discuss on Thursday, like publication bias, where the theory you're looking for is essentially what you find in the data almost because you're looking for it. Within psychology, this is called confirmation bias, which can be a real issue. So it may seem a bit of a downer that you can go through sort of introduction to econometrics and not feel like it brings you closer to the truth. That's not necessarily the case. It can do. But at the very least, we can aim for something here like Joan Robinson's goal, which is, as she said, the purpose of studying economics. It's not to acquire a set of ready-made answers to economic questions, but to at least learn how to avoid being deceived by economists. The analog here is when you read econometric papers, at least don't take as given the accuracy of the results, but perhaps think about what kind of underlying issues there could be. Think about what other variables aren't being controlled for that may skew the analysis. Think about maybe how the output variable affects the independent variable in the case of simultaneity. There are many ways in which you can further scrutinize empirical analysis and avoid being deceived, not just by economists, but econometricians. For our purposes, the takeaways are as follows. Please try to understand how we find the line that best fits, how we can think about the goodness of fit and compare different specifications or different regressions, how we can interpret the coefficients of the line of best fit, what do they mean, understand that those coefficients may be biased or statistically insignificant, in which case you don't want to prescribe policies based on them, of course. Understand at a fundamental level how and why correlation is not causation, and that determining causation can be extremely difficult. But nonetheless, also identifying, you must understand that identifying a correlation is at least the first step in investigating a macroeconomic relationship. So as you go off and you look at your own papers, try to understand if you are leaving out some other variables which may be of interest, may be important. And don't simply say, well, because we have this correlation, we will certainly be able to make policy based on this. I would like to see some awareness of the empirical sort of caveats that we have outlined here. Okay, I think that's it for today. I think this video may be longer than the other videos that I put online. I hope that was useful and valuable for those of you who are less familiar with econometrics. It will set us up for good use of data and being able to identify what might be bad use of data or misinterpretation throughout the rest of the course. That's it for today. Tomorrow I will upload a short video on how I expect the online discussions to go. This is merely housekeeping. This is the only real content video in terms of theory and empirics that I'll be releasing this week. So yeah, that's it until tomorrow. Bye for now and take care.